In a standard RAG system, a bad retrieval hurts you for exactly one turn. But when a system learns at runtime, a bad write introduces an error that the agent will trust and repeat across many future turns. Standard retrieval is a stateless lookup. Pushing a massive context window into a prompt is the temporary carriage of tokens for a single interaction. Memory operates on different rules. It is a persistent, external state governed by strict system-level policies determining how to write, retrieve, and update information. The core engineering challenge for agents shipping in 2026 has shifted. The hard problem is no longer fetching relevant chunks. It is governing what the system writes, who owns that state, and when that information should decay. Welcome back to Bearded AI Guy. Today we are breaking down Chapter 5 of the Human Architects research series on advanced AI engineering. Matej Saharia and his co-authors make a specific, testable claim. Memory now operates on a separate scaling axis, distinct from scaling the parameter weights of the model or increasing compute at inference time. Production-grade agent systems no longer treat memory as retrieval with a few extra steps attached. They establish a new baseline, splitting memory into specific families: working, episodic, semantic, and procedural, and they enforce typed persistence on top of that data. This architectural shift makes memory governance an entirely separate engineering discipline. To see why, we have to look at where retrieval ends. Major AI labs draw the line here. OpenAI separates temporary chat history from saved persistent memories. Anthropic defines memory as structured note-taking into external storage. It's a binary distinction. Memory is the specific data surviving a session closure. Letta approaches this by pinning persistent context blocks directly into the context window. These blocks stay attached across multiple discrete interactions and do not require semantic search to activate. This timeline charts the convergence. Between 2023 and 2026, both consumer applications and developer tools gravitated toward the same pattern, persisting small, tightly scoped units of governable state. Because multiple industry leaders now explicitly persist scannable units of state beyond an individual session, an active write path is a proven, non-experimental reality. Think of the agent as a colleague keeping a small notebook. They don't memorize the entire conversation. Instead, they actively choose what to jot down, so tomorrow's version of them retains the context that matters. That intuition translates to the strict technical mechanics of the 2026 runtime architecture. This schematic details the mechanism. The core is persistent external state, governed by 3 explicit policies: write, retrieval, and update. Crucially, this is distinct from fine-tuning. The outer ring shows the base model parameters do not change at all. This represents an engineering inversion. The runtime environment actively learns and updates while the model weights remain frozen. We can examine 4 primary approaches to this stateful architecture currently operating in production. They use different encoding methods and maintain different privacy boundaries, but they share the same premise. Memory is state the system is explicitly permitted to write to. This table outlines their operational limits, how they encode data, what triggers a write, and handling stale information. Claude imposes strict constraints, enforcing a 25 kilobyte preload limit. ChatGPT takes a different approach, retaining detailed deletion logs for 30 days. Across all 4 platforms, memory operates as typed, scoped, and governable data.
Dropping untyped text into a flat bucket of embeddings is an obsolete design pattern. The real leverage in this architecture comes from runtime learning. The agent tags successful past experiences. Instead of retrieving data based on similarity to your prompt, it prioritizes memories that proved useful in the past. That intuition maps to a rigorous mathematical framework, creating a trainable policy surface entirely outside of the language model itself. MemRL runs in 2 phases. Phase 1 applies a semantic filter to narrow candidate episodes. Phase 2 ranks them using a utility ranker driven by Q values. Through a reward feedback loop adjusting these values, episodic memory becomes a trainable surface. Databricks validated this in production with their Mem0 system. As labeled memories accumulated, the number of reasoning steps required fell from roughly 20 down to 5, while test accuracy jumped from near 0 to 70%. MemRL changes the retrieval objective. The system moves from searching for what is semantically closest to retrieving what is historically most effective. An active write path introduces critical vulnerabilities. A single malicious or mistaken memory write cascades. The agent repeatedly trusts that information, acting on it across many future turns. When you allow an agent to write its own memory, every summarization step becomes a risk for semantic drift. Facts distort slowly as they are consolidated over time. AI defense research categorizes 4 specific failure modes in these systems: poisoning, semantic drift, privacy ambiguity surrounding deletion logs, and scope contamination. Under idealized conditions, Ninja-style memory poisoning attacks achieve over a 95% injection success rate, translating to a 70s across different repository work trees without strict boundaries. By introducing runtime learning, developers are dealing with permanent state-based degradation. Stateless RAG architectures never experience these specific persistent bugs. This schematic clarifies the distinction between the two approaches. The purpose of standard RAG is to give an agent access to knowledge. The goal of an advanced memory architecture is to give the agent continuity. The litmus test is simple. If a system only looks up data for a single turn, it is retrieval. If it influences future turns and autonomously decides what data to supersede, it is runtime learning. Managing this state introduces persistent semantics. This is the engineering discipline of handling tenancy, versioning, redaction, and precise data provenance. Retrieval provides access to data, but governable memory provides the continuity required for true agentic behavior. RAG provides the floor. It is not the ceiling. If you want more rigorous breakdowns of AI engineering, subscribe to Bearded AI Guy. Drop a comment below and tell me exactly what kind of data you would actually allow an agent to autonomously write to your permanent memory, and what boundaries you would restrict. This research comes from the Human Architect's ongoing AI Agents in Action series. Next time, we will step into the governance layers of evaluation and feedback. Until then, remember the distinction. The read path is merely retrieval. The write path is where the real work of AI agents lives, and persistent semantics is the discipline by which they will be judged. See you in the next one.